finishing up section 6, the last section we're going to do for chapter 11 on area, and today we're going to do something completely different. We're looking at the area of regular polygons. Now I've drawn a few up here that are, if not exactly regular, pretty close. So if you remember going back to what we learned a while ago, what a regular polygon is, a regular polygon has congruent sides and congruent angles. So like for the triangle, all three angles are 60, all three sides are congruent. You keep going around the square, 4 congruent angles, 4 congruent sides. Pentagon, hexagon, I skipped the heptagon just because it's hard to draw. And here's an octagon. But so the idea is they all have congruent sides. They all have congruent angles. So there's a way we can solve these using a similar kind of logic to it, and we're going to talk about that. So there is a formula. If you're good at formulas, you can do that, but we are going to first talk about how to do it logically, so that hopefully you don't even have to memorize the formula. It just makes sense, and you can always pull this out as how to do this. The first thing is the first two, the triangle, the square. We already have formulas of how to find the area. But this can be a different way because they don't always give us the right parts we need to use those formulas. This is using a different idea. Alright, so the first thing about every regular polygon, one thing is they can all be inscribed in a circle. Now I'm going to try to draw these as best I can. Okay, get all kind of more of a sketch, but they all can be inscribed in a circle. Because of this one's going to be hard to draw because I'm too close to the top. Okay, pretend it goes up here. Okay, we have our triangle. I have to make it a little fatter. Okay, the hexagon. Alright, now again, this is a sketch. But the idea is, because any regular polygon, and you can keep going up to 10 sides, 15 sides, 100 sides, they all can be inscribed. But because of that, every polygon has a center and a radius. Now it matches the center and the radius of the circle that it is inscribed into. So let's take a look at this. I draw my center here, and I draw the radius to the vertices. See if you notice something when I draw each of these. Here's my center. Again, the radius goes to each vertex of the polygon. I think I missed that one. There we go. And our octagon here. Now, hopefully it looks like it, but if I asked you, what do you notice about all of these radii? What have we created in each one of these? Okay, each one of these, hopefully it looks like we have 5 congruent circles. Okay, we can actually prove them congruent because, first of all, they all have the same length. They're at least isosceles, right? With all the same length, and then we can actually prove that they have the same angle measure because the sides are congruent. The central angles inside here are all going to be congruent as well. So here's the logic. The idea is, if I can find the area of one triangle, we know the area of a triangle, 1/2 base times height. If I can find the area of one triangle, and I know there's 5 here because it's a pentagon, then I just multiply the area of that triangle times 5. Right? Here's my octagon. If I can find the area of this triangle, I know there's 8, so I multiply it times 8. So what we want to do whenever you have a regular figure is we're going to try to find the area of the triangle, of one triangle, and then multiply it by how many there are. So let's take a look at one of these figures and kind of look more closely at how we find the area of that triangle. Okay. Let's look at a pentagon. First, I'm going to label some of the parts that we're going to be talking about and the names that they're going to use for them. There's at least one new one. so let's take a look at it. First of all, of course, this is our center point. Okay, the center of our polygon and also the center of the circle it's inscribed in. They would call each of these a radius. Again, it goes from the center to the vertex, and it's also the radius of the circle that will be inscribed in. Okay, each one of these is a central angle. Okay, so we can find, not only do you have the measure of the angle, but it would also give us the measure of the arc, right, that it intercepts there. And lastly, if we're going to find the area of one triangle, kind of focusing on that one, we need to find, let's go ahead and write this, the area of a triangle, we already know is 1/2 base times height. So if we look here, the base happens to be the side of our pentagon. So right, so this length here, we would call a side. They're going to give you the side length, okay? But that height is something they probably might not give you, okay? So the height would be not one of the sides, but again, the perpendicular distance from the center to this side is going to be the height of the triangle. And just for fun, they rename it for you. Okay, because it's not really the height of our pentagon. We can't call it the height. So it's kind of, to not be confusing, they give it a new name, and it's called an apothegm. Okay, an apothegm. So that's our new word we have to look at. It's going to be in the formula, but it's basically, the apothegm is the height of one triangle. Okay, in our polygon. So looking at our formula for the triangle, 1/2 base times height means it's going to be 1/2. Our base is always going to be the side length, and our height is going to be that apothegm. Okay, so with this information, how we find the area of the triangle, no matter what kind of polygon it is, we can find the area of one triangle and then multiply it times how many there are. Pentagon has 5 triangles, so you'd find this times 5. If it's a hexagon, be this times 6. Okay, so this is the way I like to think of it, because then I'm not just memorizing a formula. The formula is not hard, but it's just one more thing to memorize. So this way I can, no matter what figure you give me, I know in my head I need to find the area of the triangle and then multiply it by how many there are. Okay, so let's take a look at one. Okay, we pause for our first question. Please tell me, how many triangles are formed by the radii of a regular dodecagon? Okay, let's look at our first example using a regular triangle. And I tried to draw it how you might see it in the book or in your worksheet. And we have, they give us from the center, they show us the center point. So from the center straight down means they're giving us the apothegm, which is the height of my triangle. And over here they're giving me the length of the side. Now if it helps, let's go ahead and draw the rest of the triangle in, just so you can kind of get an idea in your head what we're doing. Okay, now we said, and if you want you could draw all 3 of them, but if you want to just focus on one, that's fine too. Alright, so we know we're going to find the area of our triangle, and then at the end there's 1, 2, 3 sides, so 3 triangles is what we think of. Alright, so the area of our triangle is 1/2 base times height. Remember, we said it's going to be 1/2, the base is the side, so we're going to do the side, and then our height is the apothegm. I just want to write that out one more time. Okay, and since there are 3 triangles, let's go ahead and just do that in the whole thing. The area of our large triangle, let's do large triangle, our regular triangle, is 3 times whatever this was. 3 times 1/2 times the side times the apothegm. Okay, so when we fill that in, 3 times 1/2, our side length is 12, and our apothegm is 3.46. Let me go grab my calculator. Okay, I'm back with my calculator. Let's take a look at our numbers here. When I see this, first thing I would say is let's take half of 12 because it's a nice even number. So we wind up with 6 times 3, so we have 36. Then times 3.46. So our area of our entire polygon is 124.56. They don't give us units, so we would just say units squared. Okay, so now let's take a look at what we've got and see how it matches with the formula that they give you. Okay, so I'm going to erase the numbers and just kind of look above here. Okay, I erased our numbers. We're back to where the formula we had up here, where we said we had 3 triangles times the area of the one triangle, 1/2 base times height. And then what they did is they said, all right, we know that whatever number this is, that's the number of sides, and times the side would give us the perimeter of our figure, right? So if it's a 5-sided figure, it wound up being 5 here. 5 times the length of one side gives us the perimeter. So I said, let's combine this to be the perimeter. And then that's really kind of all they changed, but then they change it and they say, all right, my formula for any polygon equals 1/2 AP. Okay, there's our formula. They say I find 1/2 times the apothem, which we know we have to find, times the perimeter. And that's fine if you want to use the formula, you got it in your head, you know, okay, 1/2 AP, 1/2 AP. That's fine, but you have to find the perimeter. So they're going to give you the length of the side. You have to know how many sides you have to get the perimeter. Again, for me to keep it in my brain and use it over and over again, I always just remember, all right, I got to find one triangle times how many there are. I don't care which one you use, just whatever makes sense to you. So let's look at another example. Here's question number 2. Tell me, what is an apothem? Okay, here's our next example. We're looking at a regular hexagon, and they start getting interesting because this time they didn't give us the apothem and a side, which are the 2 parts we need. They gave us the apothem, which was nice, but they gave us a radius. They gave us a radius of 8. So we need to find that side before we even get to our formula of 1/2 AP or finding the area of our triangle. All right, so what you have to do is pull back from your memory, how do we find this? The nice thing is each one of these triangles, when you drop the height there, the apothem, it gives us 2 congruent right triangles, okay? So in this case, we have the hypotenuse of my right triangle. Let me go ahead and kind of highlight it here for you, looking at this triangle. Okay, they give us the hypotenuse and one of the legs, and if we can find this leg, we can find our side, because there's 2 of them, right? Remember, in an isosceles triangle, when we drop the altitude down, it cuts it in half. We have lots of names for that little part there, don't we? All right, so what we want to do, this one we notice, all right, I have 2 sides of a right triangle. I can find the 3rd side, pulling out my Pythagorean theorem. So I can say 6.5 squared plus x squared equals 8 squared. I'm going to go ahead and move everything around, put the 6.5 squared over there. X squared equals 8 squared minus 6.5 squared. Let's get out our calculator. See what we have here. 8 squared, 64, minus 6.5 squared. 21.75, actually I did this subtraction already, didn't I? 21.75 is my x squared, and then we need to find the square root. So our x is actually 4.66, okay? 4.66. Now remember, that's only half of my side, so I'm going to go ahead and write this. My side actually is 2 times 4.66. It's better with the x. Alright, so times 2 is 9.32. Let me round that up. I guess it rounds up to 9.33. Okay, so that is our side. Now we have the parts we need. I'm going to do this one with the formula. The area of our pentagon is 1/2 AP, where again, A is the apothem, P is perimeter. So we have to figure those parts out. We know the 1/2 is pretty good. They gave us the apothem as 6.5, and our perimeter is our length of our side times the number of sides. So 6 times 9.33 is my perimeter. You can go ahead and plug that in your calculator. So 6 times 9.33, this is 55.98, times 6.5, and the last thing, let's divide by 2. 181.94. Again, we have no units, so we'll just call it units squared. And that's the area of, and I called it a pentagon, didn't I? It's a hexagon. Oops. Okay. Area of our hexagon. All right. Let's try another one because they try to make it even more interesting. Okay, let's look at one that's a lot more exciting because this time they tell us we have a heptagon with side length 7. Okay, so we don't have the apothem that we need in order to use our formula or define our triangle. We need the apothem times the base, the height times the base. So we have to find our apothem. So let's draw a little line here to represent the apothem. I knew it was going to be kind of crooked. There we go. That's what we're looking for, is our apothem. Okay. Now this time we know we have, this is 3.5. Let me go ahead and draw the triangle over here. Just a little so you can see a little better. Here's 7. Here's my apothem that we need. And we already know because it's an isosceles triangle, we know that this side is 3.5. So we've got one side of our little right triangle, but that's not enough to use our Pythagorean theorem. So we have to pull back again, and we're going to be looking at trig. Okay, so first of all, don't forget your SOHCAHTOA. I'm going to write that up here. All right. In order to find this side, the apothem, we have, what we want to look at is looking at our angles. Okay, so if I know this angle, which I can find, then I can use the tangent because it's opposite over adjacent is where we're going to go with that. All right. So the idea, first of all, how do we find this angle? So you're going to get a couple problems tonight where first they tell you, can you find that central angle? Remember we talked about whenever you have how many sides you are and you draw the radii, you're going to get, in this case, it's a 7-sided figure, so it's a heptagon. We have 7 triangles. And how do we find that central angle? So the first thing you want to do, you know, all together they add up to 360, so we're going to take 360 and divide it by 7, and that'll give us our central angle, right? Let's go ahead and do that. 360 divided by 7. So we know the angle measure for the central angle is 51.4. Now, of course, we're cutting that angle in half for our triangle, so you have to watch this. This is a couple-step problem here. The angle we're going to look at is we need to divide by 2, and we get 25. So where do we write this one? 25.7 degrees is one of these angles, okay? But now if we know that, we can find our apothem using our tangent. So we say, all right, the tangent of my 25.7 degree angle is 3.5 over A, the apothem I'm looking for. So if you remember when we solve for A, we're going to multiply both sides by A. It's going to cancel over here. So I have A equals 3.5 divided by our tangent, 25.7, because we're going to move him, divide both sides by that. And our apothem then is 3.5 divided by, hit every number I can, divided by the tangent of 25.7, hit my tangent. You know what, I'm in radians, which is not going to help me. Let's try it again. 33.5 divided by tangent of 25.7, and we get 7 point, we'll go ahead and round it to 7.3. That's my apothem. Alright, Now I have the apothem, I have the length of the side, so I can go back to my formula, the area of the heptagon. This time I'm going to go ahead and do it the other way. I'm going to find my area of my triangle, and I know there's 7 of them, so I'm going to go 7 times 1/2 base times height. My base is my side, which is 7, and my height is my apothem, 7.3. Alright, let's go ahead and multiply all that together. 7 times 7 is 49. And we have times 7.3. I think I hit something wrong. There we go. Then divide by 2. 178.85 or 0.9 units squared. Now again, you could use your 1/2 area is 1/2 AP, or you can find the area of my triangle times 7, whichever one works for you. Okay? Alright, let's look at one more little thing about finding our angles, just to make sure we got it. Alright, I just wanted to go over finding the angles of different regular polygons with you. Again, this one you might, you're just used to looking at the square, but I want you to think of it differently as a regular polygon. Remember, if they ask you for the central angle, there is a center of our square, and what they're looking for is the angle measure at the center. Alright, so if they say find the central angle, you're going to go ahead and take 360, divide by, we got 4 triangles, so our central angle is going to be 360 divided by 4, which is 90. Alright, they also then may ask you for these angles down here. Now remember, every time, even when we draw the pentagon over here, our triangles are always isosceles. So that means that we're going to divide whatever's left over from the central angle. Every triangle has 180 degrees, so we subtract that. This time we're subtracting 90. That leaves us 90 degrees. Split it in 2. So we have 2 nice 45-degree angles here. Okay, they might ask you those angles as well. Okay, let's look at our pentagon here. This one's, you might not know off the top of your head, so let's go ahead and work it out. We know all 3 of the angles, since it is inscribed in a circle, is up to 360, so you're going to divide 360. There's 5 triangles, we're going to divide by 5. So 360 divided by 5 gives us 72 degrees. That is our central angle here, 72 degrees. Central angle. And then again, it's isosceles, so we know that all 3 angles must add up to 180. So we're going to subtract 72 from 180. That leaves us 108. Divide by 2, that means we have 2 54-degree angles here. Okay, so those are the things that, the types of angles they might ask you. Okay, thank you for hanging in there through all the examples for 11.6. We are finished with all material for chapter 11 that we're going to be looking at for our test. And I want to give you our joke of the day. So what kind of tree does a math teacher climb? A geometry. There you go. Alright, we will be reviewing everything this week, finishing up the week with a test. Okay, I will be posting the test on Thursday at 3, unless you tell me of a time you want to take it other than that. So I will look forward to see you on Zoom this week. Talk to you later.